Good morning. Let's get started. All right, so let's finish that variation of parameters approach. Okay. So in the last lecture, I have derived some formulas for a new approach, which is called variation of parameters, to solve for a nonlinear homogeneous, linear non-homogeneous second order ODE. So when you have an equation like this, its homogeneous solution is this. Okay, we can let our yp, okay, the particular solution, equal to m1 times y1, m2 times m2. Okay, m1, m2 a time function, a function of the parameter t. So that's why they call it variation parameters. Okay. And we have gone through the process, okay, and we find that the m1, okay, equal to, okay, this one. And m2 equal to this. Okay. And wt is a so-called Wronskian. It's a determinant. So basically you get y1 of t, y2 prime t, minus y2 of t times y1 prime of t. Okay, let's keep it down, okay? So that's your Wronskian here. Okay? So basically, when you solve this second order ODE using variation parameters, this is the formula. Okay? Write it for now. You know, just write it a few times. It'll be yours, right? In the final, I think I'll give this to you. Okay? Yeah. So let's take a look at a couple of examples. Can you two not talk to? Okay. Okay, so this is a function. Okay, this is the ODE here. Okay, and for this ODE appearance, you see your f of t equal to second t, and second t is 1 over cosine t. Okay, and this is obviously not in that typical format that we can use the method of undetermined coefficient, right? Because this is not a function in sine cosine, it's not a function in exponential, a function in the polynomial, right? It's 1 over cosine. So we had to use this variation of parameters to solve for this question. First step is still have to solve for the homogeneous solution. Okay. Set up the characteristic equation. You get two complex conjugate roots. Okay. So y1 of t is cosine t, and y2 of t is sine t. Okay. So then your yh is c1 y1 plus c2 y2. So c1 cosine t plus c2 sine t. Okay, that's as usual, right? And now we're going to use the formula right here, okay, to solve for our yp. But first we had to solve for M1 and M2, and then we can get YP. So let's solve for M1 and M2 using the two formulas. Okay, so first you need this Wronskian WT at here. So Wronskian is Y1. So if you look at this Wronskian here is Y1. Basically the Wronskian, let me write it in the matrix here. Okay, so it's the determinant of this matrix. So Y1 at here, Y2, Y1 prime, and Y2 prime. Right, so that's what Wronskian is. It's probably easier sometimes you memorize this 2 by 2 matrix and then calculate the determinant. Right? Okay, so the Wronskian is the determinant of that 2 by 2 matrix. And then we calculate, okay, plug in the Y1. Y1 is cosine t, Y2 is sine t. And Y1 prime is negative sine t, Y2 prime is cosine t. Okay. So cosine times cosine minus negative sine times sine. So that gives you a cosine t squared plus sine t squared. And this determinant end up just 1. Okay, that's very simple Wronskian. Once you get the W, we'll plug it back to M1, M2 formula. Okay, then to calculate the two integrals. Okay, so let's calculate M1 first. Okay. All right, so W is 1, and Y2 is sine. F of t is 1 over cosine. Okay, that's M1. And this is negative sine over cosine. dt. Missed the dt here. Okay, so sine, cosine, what's the integral of this? Or what technique can you use? Substitution, right? Yeah. You know, my way of doing this is always basically I move the sine into the d there. So cosine t's derivative is negative sine t. Right, so that d cosine t is equal to negative sine t dt. Okay. It's the same as a substitution basically. Okay, but this way I have cosine at here, so it's like a 1 over u du. So that's basically lowering cosine t. Okay. Absolute value. In this case, you don't need plus a constant. Okay, we don't need a constant here. Okay, and because we're going to multiply the M1 back to Y1, right? So we don't need a constant. We just need a specific function of t. Is it okay so far? Okay, so you can calculate M2. One at the bottom. Y1 is cosine, and f of t is 1 over cosine. That's even better. So everything cancelled, and you end up just 1. Okay. So once you get this, you plug it back to yp, m1, y1, m2, y2. Overall is ln cosine t times y1 cosine t 1 times sine t. So that's your yp. Just a second here. Is it? Sorry. So what's t, right? T. T times sine t. Okay, so then your general solution is your YH plus YP, right? And you get your general solution. And if you have initial condition given, then you can solve for C1, C2. Okay, that's basically the same as every other question. Okay, so this approach, I think it's not a difficult approach. Okay, it's a basically application of this formula. Right? And when do you use this approach? You use this approach when the function, okay, is not in the format as given in the undetermined coefficient method. And you can use this approach. Now, even better, actually, you can even use this approach even with this function is in the format as in the undetermined coefficient approach. So, for example, right? If I have a y double prime plus y equal to sine 2t, okay. Now this sine 2t is sinusoidal curve, a sinusoidal signal. So you can use that undetermined coefficient, right, to solve this question. So basically your yp, your choice of yp, okay, but it would be a times cosine 2t plus b times sine 2t, okay. And then you can solve for a and b, right? Now you can also use this variation of parameters to solve this question too. Okay. And sometimes maybe it's actually a little simpler, right? But depends on how comfortable you are with integration, right? Because you're going to have to deal with integration right here. So maybe let me quickly show you how do I solve this using variation of parameters. Okay. So first example, in lambda, first one, I'll obtain the characteristic equation. Okay. So this is the same characteristic equation as in the previous example there. So your YH equal to C1 times Y1 plus C2 times Y2. So C1 cosine t and C2 sine t. And I can see myself a little bit trouble. My Wronskian is exactly the same, so which will be the 1. Okay, that's exactly the same as previous question. Okay. So let's try to calculate M1 and M2. So I'll try M1 for you, and then you can try M2. M1 of t is negative y2 f of t over the Wronskian dt. Okay, so let's plug in all the numbers. y2 is sine t. F of t is sine 2t, and then dt. Okay, so this integral basically you have a negative here, sine t and sine 2t dt. Now this is the part, if you're not comfortable with the integration, then you probably shouldn't use this approach. You can probably use the undetermined coefficient, because over there's no integration, right? It's all about the derivative. Okay. But this is not a very complicated integral. So sine 2t is 2 times sine t cosine t, and that's negative 2 sine t squared cosine t dt. Okay. Again, you can use substitution technique. Okay. But if I do it my way, and I will have d sine t over here, because d sine t is the same as cosine t dt square. Okay, so now you have a u square, so you get 2 over 3 sine t to the power of 3 negative. Okay, so that's your M1. Right? And you can try M2. similarly, you get to m2. So m2 you get negative 2 over 3 cosine t cubed. Okay, yeah. So put them together, and then you get the solution. All right, yeah. Okay, so basically we only have two different approaches for solving second order non-homogeneous ODE. Okay. They all follow very strict rules. Essentially, undetermined coefficient, you look at the format of the inputs, then you look up the table, right? Then you get the solution. Variation parameter, you have the formula, plug into the formula, get the Wronskian, get everything, do the integration, you get a solution. Okay. So very standardized approach. And there's nothing tricky there. I think once you practice a couple questions, you will feel much more comfortable. Okay. Now technically, next usually I would like to talk about is actually forced vibration. Okay. So forced vibration means if I have a mass spring damper system, for example, okay. But I would not talk about this because I think we're kind of running out of time. MBC equal to this, right? So when you have, let's you change it to X here. Okay, so we typically use X for a mass spring damper system. Okay. When you have a mass spring damper system, you have a second order ODE basically like this. Okay. Now in the previous lecture, we have talked about when this is 0 here. When this is 0, if you recall that, we call this as a free vibration, right? But now, if you have an input here, basically, okay, so K and B, MBK, so why do I put a C here? MBK, yeah. And then you have your displacement, and maybe you have an input over here. Okay. Now this time, this is called forced vibration. Okay. So if you look at this differential equation, it's nothing different. Nothing different from what we have all the examples that we have solved, right? It basically is just a typical second order non-homogeneous ODE. Okay. But we can relate this to an actual vibration example, basically. If this is a different signal, how does X move, right? How does this system vibrate? Okay. Now this is the part I will actually I will skip that. I will keep it as a self-study lecture notes for you to read it, okay, on Canvas. Okay. So you can read it. You may find that a lot of symbols flying around. But just always keep in mind, it's the same differential equation, right? Nothing different from a regular second order differential equation. Okay? We just gave it a different meanings, essentially. Okay? So I want you to take a look at yourself, okay? In terms of the subject of forced vibration. Okay? So forced vibration, in essence, when you read it, okay, just remember, I think I had a discussion with one of the students. Every system has a natural frequency. So the question is always, what happens if my input signal getting close or even be exactly the same as the system natural frequency? Right? That's basically the whole idea of vibration, right? As for a simple system. When your input frequency, okay, is close to the natural frequency of the system. Right? Natural frequency, if you recall that, is what, K over M square root, right? The natural frequency. Okay. Now what happens is you will have the so-called resonance. Okay. So resonance means the whole system starts to vibrate really fast, really quick. Right? We've seen that maybe in many different cases. When you have appliance not installed properly, right? And then when it's running, the appliance, you feel the vibration, right? Yeah. And sometimes it vibrates really hard, sometimes not. Okay. So if you install it properly, perfect, but if you don't install it properly, then maybe it starts to vibrate really hard, especially like washing machine. Right? So this input frequency, right, will force the system vibrate. If the input frequency is too close to the natural frequency, then it will actually causing this a really detrimental type of harm to the system, which we call the resonant. Right? And one of the engineering example we always use is the Tacoma Bridge in Washington State. Okay? It's a bridge that broken down because of the wind. So the wind blows on the bridge, and literally the bridge starts to resonate with the vibrating of with the input of the force from the wind, and then immediately the bridge basically broke down. Right? Yeah. So that's an example of steady vibration and the relationship between the input frequency and the natural frequency of the mechanical system or electrical system, any system, right, by itself. Okay. So take a look at that lecture notes. I'll put it on the canvas. Okay, you can self-study that part. Okay. So we're not going to test too much, but I think there's one Simon question similar to that, so you can take a look at the solutions too. What I want to move on to is Laplace transform. Okay. So from this until the end of the term, okay, and my past experiences, it will be very difficult to actually focus because it's going to be just very pure mathematics, okay? Even more pure than the previous lectures. Okay? So I need to buckle up. When if you feel too bored, that's okay, but just don't give up, right? Okay. Definition. Okay. So always start from definition. Let's say we have a causal function, f of t. Then its Laplace transform, okay, we denote it as capital F of S, or with this kind of symbol. So I'll write it again. So this is basically an L symbol. It's like a Greek letter L, but if you don't like, you can just write a capital L. That's fine. Okay. Yeah. So this is essentially an operator now. Okay. So I'm going to talk a little bit more here. Okay. Denote this, then the f of s is calculated by the following formula. Integration 0 to infinite f of t e to the power negative st dt. There. That's Laplace transform definition. Okay. So what's going on here basically? If you consider Laplace transform as certain kind of a system, and we can consider L as an operator, right? So the L here is an operator. You give the system a time function. So this is a t domain. Okay. So function f is a function of t or time. You put it into this system, represented by the operator L, and it spits out a different function. And now this time it's a function of s. Right, that's basically what's going on the paper. And this is in the s domain. Okay. And that's why it's called transform. So the system in here, which is the operator L, transforms your original function of t into a function of s. Now your immediate question is, what's the point of doing that, right? Yeah. By looking at this, just looking at this, probably there's really no point of doing this. But later you will see there are so many good things about this. But the fundamental point is, right? The fundamental point is this. When human beings study things, we try to study things from different perspectives. It doesn't work in this perspective. Let's work from the other angle, right? And the other angle will probably give a completely different understanding, right? Or maybe even better understanding, right? So this is basically what transform at here, right? All about. And there are different transform in mathematical domain. There's Laplace transform, and later we're going to learn Fourier transform, and there are many other different transform, right? So that's the whole point. The different transform give us a different perspective, and we'll see how the Laplace transform can give us a new perspective in solving engineering problem. Okay. Now, for example, right? I'll give you a simple example here. Let's say this is not Laplace transform. For example, I'll ask you to calculate. Can you calculate u times v? Right. So you calculate u times v. Right? That's one direct approach. Okay. But I can also do this. If I apply lawing, if I apply this lawing operation, then this becomes lawing u and plus lawing v, right? So then this approach here, I'm not calculating multiplication anymore. Now this time you're calculating what? Addition, right? So people may like addition. If you have a calculator, you can calculate lawing, then plus the addition. That addition is better than multiplication. Okay. So this is basically an idea of a transform. Okay. And this is, of course, a little bit more complicated transform, right? Yeah. So we're going to look at Laplace transform, okay, and we're going to look at some typical functions. So if I plug in some typical function at here, then what would this Laplace transform spit out on this side using this formula at here? Okay, so we'll look at that. And the other thing before we move on at here, so you notice that we have this s at here, right? The s. Okay. So this is integration about the t, so s is considered as a constant. Now the s at here, okay, is actually a complex number. It's a complex number. Complex number means s can take as sigma plus j omega, so real part plus the imaginary part. So that's what s is. So you need to keep in mind, s is not a real number. I mean, s could be a real number, okay? But s in general is a complex number. Okay? So not just a real number. Okay? That's s. And the other thing is this L, okay, operator. Okay. This Laplace operator is linear. Okay. It's a linear operator. It's a linear operator basically means you have the superposition rule will be satisfied. So if you plug in C1 F1 Ft plus C2 G of t, then you should get C1 Laplace f of t C2 Laplace g of t. Okay. So it's superposition rule. Now if you recall, I think at the beginning of the term, and I said we're going to learn a few operators, right? Laplace is one operator, and in 248 we're learning the greeting operator, okay? And later, very soon, we're going to learn so-called curl operator, okay, a del dot. There's also a divergence operator, okay. So there's all different type of operations essentially, okay. And the next one, I'll write it, but you don't have to worry too much. We're not going to actually use this in our lecture, okay. The inverse of a Laplace transform, which means if I have the function f of s, so you already have the transform. You have the transformed function f, and you want to get back to the original time function small f. So that's called inverse Laplace transform. Okay. So mathematically, the inverse Laplace transform takes the form of this. Okay. Now this is by far probably the most weird type of integral you ever seen, right? You have a complex number here, then you have sigma, you have infinite, right? And this is actually another branch of a calculus. It's called the complex calculus. Yeah. So anyway, so we're not going to deal with that. Don't worry about that. Okay. I did see the journey of calculus for you, mostly for engineering student, will stop here, right? It'll stop not just here, it'll stop in the other course, okay, in second year. But if you move on to graduate study, then you probably learn something like this, okay, complex integral calculus. Okay, so I want to show you is a Laplace transform of typical functions. So we'll look at some very useful function, and then what are their Laplace transform? Okay, what do they look like? Okay. So I'll show you quite a few of them. So first, let's look at this function. So let's say if we have a function take a form like this, exponential function. Depends on the value of a, could be exponential decay or exponentially increased function. Since we have learned the unit step function, right? So when you have a piecewise function written like this, you can also use the unit step function to simplify its writing. So basically, you use this times the u of t. That's the same meaning as this piecewise function. U of t equal to 0 when t is less than 0, and u of t equal to 1 when t is greater than 0. Right? That's exactly the same as this. Okay? Yeah. Okay, so what is the Laplace transform of this function and here? We will use the definition of Laplace transform to do the calculation. Okay. The definition is listed at here. F of t and e to the power negative st and dt. Okay. So f of t is the function you're transforming. Now technically I should write the u of t at here, and then e to the power negative st dt. Okay. However, because the integral is 0 to infinite, so when t is between 0 to infinite, the u of t is always what? 1, right? So you don't have to keep this one here. Okay, so that's basically 1. So we're just integrating a times e to the power at negative this, just integrating this one. Okay, this integral is actually not difficult because we're integrating t, so you're going to consider s as a constant. You can combine these two together, becomes basically e to the power negative s plus at and dt. And the results of this integral, that's just an exponential function. It's a over s plus a, and e to the power s plus at 0 to infinite. There should be a negative here, right? There should be a negative here. Okay? Yeah. Okay, so now we can plug in the infinite sign, okay, into this integral here. So what do we get? So negative, I'll put a negative on the side here. I'll put this whole negative on the side. Okay? Yeah. So that's the integral, the results after you plug in the limits. And the second one is 1. Okay, this is just 1. And the first one, right, the first one is what? So let me deal with the first one here. So e to the power negative s plus a times infinite. Okay. And what's s again? S is sigma plus g omega is a complex number, and then infinite, right? Yeah. So I can separate this term into e to the power negative sigma plus a times infinite, and then e to the power negative j omega times infinite. So I write it as infinite, but you can consider this as a really, really large number, right? So this one here is a really, really big number. Okay. Same here. Is that good? Yeah. So now, if I look at these two exponential functions, this is a big number. Okay, it's a very big number. But it doesn't matter how big this number is. When you have a e to the power j omega times a big number, any number, right? This one is what? This is basically cosine omega and negative omega that angle plus j and sine, then omega that number, right? So what this essentially is just complex number with some oscillations, right? Yeah. So that we can't do anything with it. So this is essentially a complex number. Well, end up with a complex number. But over this side here, e to the power negative sigma plus a times infinite, positive infinite. Okay? Yeah. Under what condition this will go to 0? Right? Under what condition this will go to 0? When sigma plus a greater than 0, right? If this is greater than 0, then this guy will go to 0. If this guy go to 0, then the whole term go to 0. Okay? Yeah. So basically, when sigma is greater than negative a, then this whole term will go to 0. That make sense? Yeah. And this is exactly what we want. So this guy at here, okay, we call it, okay, basically sigma is the real part of that s. Okay, the real part of the s here. And when the real part of the s is greater than negative a, in this case, it goes to 0. And this is what we call is the region of convergence. Okay, region convergence. Only when it is in this region, then that term go to 0. And when this term go to 0, the Laplace transform, right? You have the first term go to 0 now. You only have the second, the coefficient times negative 1. So you will only have what? Laplace transform of the regional one is a over s plus a. Okay. So you get this basically. Okay. So in the future, okay, in this example I showed you under what condition you'll get this, right? You'll get this. And this is called region convergence. But in the future, I'm going to actually neglect this region of convergence. So for every Laplace transform, there will be a region of convergence. Honestly, we don't have to care about that. So we can just consuming, I definitely have a region convergency that will give me this results Laplace transform. Okay? Yeah. But that's not our concern. Which one and what type of region convergency would be. Okay? But in this case, now you get it, right? When you have exponential function in time domain like this, it's transformed into a over s plus a. And that is a very common type of a function. Okay, very type of common function. Okay, especially if you set a equal to 1, right? It's just an exponential function. Okay. So let me show you another one here. Okay. F of t equal to unit step function. So what would be the Laplace transform for the unit step function? Unit step function, basically you multiply f of t over here, and unit step function is 1. So you don't really have anything except 1 at here. Then the integral just about e to the power negative st, and that's 1 over s. E to the power negative st is the result of the integration. Then you plug in the limits of the integral here. Okay. So when I plug in infinite to the t, right, that's where I care about the region of convergence. Assuming in the region convergence, when you plug infinite into here, it'll go to 0, right? So only 0 here, so that get 1 over s only. So that's why we don't have to care about the region of convergence anymore. Okay? We only have to assume when you plug in the infinite over here, right? When you have a e to the power negative something, it's going to be 0. Okay? So your unit step function, its Laplace transform is 1 over s. Okay, 1 over s. So I will show you a couple more, but not all of them. Okay, so let me show you this one here. Let's look at f of t equal to sine omega t. What will be the Laplace transform of this function? Okay. Now in this one, I'm not going to use the formula. I'm going to use the results that we have just derived to obtain the solution at here. Okay? Yeah. If you recall that the Euler's formula, e to the power j omega t equal to cosine omega t plus j sine omega t. Okay, so that's Euler's formula. Okay. So then, if I'm going to take Laplace transform of this e to the power of j omega t. Okay? Yeah, forget about sine first. Let's just say what is the Laplace transform of e to the power j omega t. So what do? I'm actually going to go back to my first example. I have Laplace transform of this, right? So let me write it here, just do a comparison in here. So Laplace transform, let's get rid of the capital A here. If I just take Laplace transform e to the power negative at, I get 1 over s plus a. So how can I use analogy? Then what will be the Laplace transform of e to the power of j omega t? Yeah. So what would that be actually? S what? Plus, but this is negative. minus, right? So you can write this one as e to the power negative j omega t, right? Yeah. So this negative compared to that negative, and then this negative j omega is that a. So then you get this, right? Yeah. Good. Okay. And then from here, I can simplify this complex, okay, this number, okay, this one here. What you do is basically you multiply the bottom with its conjugate, okay, and then you get bottom here, you get s squared plus omega squared, and then you get something like this, okay, if you expand it. This is the exponential e to the power j omega t's Laplace transform. So how is that related to the sine and the cosine? Let's get back to the Euler's formula here. Okay, so this Euler's formula right here. Okay. So if I'm going to take Laplace transform of both sides of this equation using the linearity, it's the same as the same as this. So Laplace transform of E is equal to Laplace transform cosine omega t plus j times Laplace transform sine omega t. Okay? And we already obtained Laplace transform of this exponential one, which is this and that. So if you compare, which means the Laplace of a cosine is this, and the Laplace of a sine is this, right? Yeah. So that you get the results of Laplace transform for cosine and sine. Okay? Yeah. So I'll show you a couple more, and then we'll look at applications of Laplace transform.